All right. So hi everyone, I am Ritojit Kundu, a PhD student at IIT Kanpur. So I am one of the TAs in this Advanced Quantum Mechanics with Applications course. So this week we'll be talking about week 6 content, which is essentially approximation, which includes perturbation and also variational principle. So I have prepared few problems which will in turn help you to solve the actual assignment of week 6. Okay. So before starting, let me just confirm, is my screen visible and audio clear? Can anyone confirm it? All right. Okay, so the plan is, so we'll talk about few problems of perturbation theory. So the problems, let me just briefly tell you what the problems we'll be discussing today. So one of the problem is it is about degenerate perturbation theory. Okay, where the two states here are perturbed. I mean they are degenerate, and there is additional some small perturbation which you have added, and then you will see that what are the new perturbed eigenstates or the energies of those eigenstates. So then we have some another Hamiltonian with a perturbation CLY. So this is the Hamiltonian of a rigid rotor in a magnetic field, where this C is something like magnetic field. So here we want to find the lowest order non-vanishing perturbed energy. Okay, and then we'll be talking about some problems in hydrogen atom. So here we'll be studying quadratic Zeman effect. So in most of the cases we ignore this term because this is so small. So this Hamiltonian we don't take in our when we normally study this system. So now this is like a perturbation to our H0 Hamiltonian, and so we want to study that what is the change in the ground state, change in the energy of the ground state. Okay, and then we'll be talking about some problems in variational principle. For example, I'll give you some potentials, and I'll ask you to come up with a solution, come up with a trial solution, and try to calculate the energy of that ground state. Okay, and then so we'll just, this is for a practice in 3D. How does this variational principle work out? So we'll start with an trial solution, trial wave function of the hydrogen atom, and then we'll look into the variational principle of it and estimate the ground state energy with that method. And at the last, I'd like to finish with this variational principle for excited states also. Okay, so we'll see what does that mean. So at any point, if you have any questions, so please, you can unmute yourself and you can ask. Okay. Okay, so the first one, this is about the degenerate perturbation theory. Okay, so now we are given a Hamiltonian. Okay, so we can write the Hamiltonian as H0 and V, whereas the H0 is my diagonal Hamiltonian. Okay, so diagonal means I know all of the eigenvalues and I know all of the eigenvectors, and on top of that there is a additional V. So V has small parameters like A and B. So this A and B, these are very, very small than this E1 minus E2, these parameters. Okay, so this V is our perturbation to the H0. Okay, and you will like to see that, okay, with the addition of V, what happens to the energies of the eigenstate. Okay, so for H0 has energies E1, E2 and E3, and the eigenstates you can find out, these are just 1 0 0 or 0 1 0 or 0 0 1, this kind of vectors. Now let's start with the perturbation theory. So like this, because this is a degenerate, Hamiltonian is a degenerate, has a degeneracy at E1 energy, right? So the first tactic is to try to diagonalize that first, the degenerate part. Okay, so here this is the H0's first block. So this is what I am calling as the degenerate subspace. So it means the subspace which has the vectors of those degenerate states. Okay, and this is the same block coming from this V matrix, right? So now our task is to diagonalize this matrix, but we see that this is already diagonalized. Why? Because the V, this block, all of these things are 0. Okay, So in first order, we'd like to diagonalize this quantity, but this is already diagonalized. Okay, so first order, the degeneracy is not lifted. Okay, so we need to look into some further other orders like second order. Okay, and we'll have to do this business until this degeneracy is lifted. So okay, first order we could not lift the degeneracy. So now we have to go to the second order in this perturbation theory. Okay, so in second order, for this degenerate perturbation theory, what we do is we look into a matrix like this. Okay, so this matrix has on the numerator these terms Vim and Vmj. So these are matrix elements of the perturbation which we have added onto our Hamiltonian, and this Ei and Em, these are the energies of our bare Hamiltonian or H naught. Okay, and here the summation is taking place on M. Okay, but we have to make sure that M is not same as I or not same as J. Okay, so this is the matrix we have to form from this V matrix and the eigenvalues of our H naught. Okay, so for example, this gamma or lambda, capital lambda 1 1 in this case will become something like this, V1m and Vm1, like V1m and Vm1. So you can go ahead and look into the matrix that this V, there are only this part which is sitting here, which will contribute to the summation. Okay, so that's why I have written V13 and V31. Okay, and on the denominator I have only E1 and E2. Okay, so just remember this E1 is the energy which has degeneracy, and the E2 is the other energy. Okay, so this is what my capital lambda 1 1 is for this system, and then lambda 1 2 will be given in the same fashion, but the terms will be different right now. So V13 and V32. So I mean, we have to just carry out this computation, right, and we will find out different elements of this matrix. Similarly, we can find out this gamma 2 1 in this case, okay, which will be V23 V31, and lastly we will find out V23 and V332, which will contribute to my gamma this lambda 2 element. Okay, so now after I have done all of this calculation, I can write this this quantity in a matrix form. Okay, now if that is the case, then so I have just written all of these parts here, and so now task at hand is to find the eigenvalues of this matrix. And if you will be able to find the eigenvalues of this matrix, then you know what are the corrections to your energies in the degenerate subspace. Okay, so how do you evaluate the eigenvalues? So we calculate something called the characteristic equation, so which is given by this matrix for which we are trying to calculate the eigenvalue, and the energy which will be replaced by the eigenvalues, and this is the identity matrix. So you go ahead and write the determinant. Okay, so determinant looks something like this. So you can see that this has nice this is Hermitian, okay, nice properties are here. Now you can go ahead and diagonalize. You can find out this characteristic equation, which is a polynomial in this variable E. Okay, and you have to solve for capital E. So okay, so you just calculate the determinant. So this determinant, this multiplies with this. Okay, so that's why I get the first term, and this multiplies with this, so that's why I get the second term. Okay, but there is a minus because we are calculating a determinant. Okay, and this has to be equated to 0, and we have to solve for capital E. Okay, so now there are some algebras, so let's just go ahead and look into those algebras a little bit. So you can multiply these two parts. Okay, and you will get something like this. Okay, and here what I have done is I have divided the whole equation by E1 minus E2. Okay, E1 minus E2, it should be square. So now you can expand these two parentheses and you will get something like this. Okay, and you will see that this last term which was sitting here, we cancel with this first term, and then you can take this E is common. Okay, and you will see that okay, E, one of the solution of the E is actually 0. Okay, and the rest of the other solution, so there this is a second degree equation, second degree polynomial. So one solution is 0, so we are only left with one other solution. So the other solution, you can just solve this part in the square brackets, solve for E, and you will find out the other solution is just this A mod square plus B mod square divided by E1 minus E2. Okay, so these are the two eigenvalues of your gamma matrix. Okay, so now now let's just write what are the new modified energies of all of the states. Okay, so E1, the initial energy of the H naught, one of the state 1 has energy E1, but after adding perturbation and after doing the second order perturbation analysis, we found out that there is this additional correction to this energy. Okay, but one other state which also belong to the degenerate subspace does not get corrected at all, so it remains as it is. Okay, but we have not yet calculated the E3, the third, or this was the E2 in your Hamiltonian. So now let's calculate this E2. Okay, so now see that this 3, like the Hamiltonian started with this 3. This E2 was not a degenerate state, right? So in H naught, this E2 was a simple state. It didn't have any degeneracy. Okay, so for that case, for that state, we can directly apply non-degenerate perturbation theory. Okay, which I have done here. If you calculate the this perturbation order, you will see that in the first order there is no contribution, and all of the contribution are in the second order, and this is calculated using the non-degenerate perturbation theory. Okay, which is actually much more simpler than the degenerate perturbation theory. Now, so how do we know that this result is correct or not? Okay, so there is a way to check our results, which in practice you should all try to check. So how should we check it? So we had our Hamiltonian total H, right? So which has this E1 and E2 and A and B star, all of those things together. Okay, so it so happens that for this 3×3 matrix, the characteristic polynomials we can solve. Okay, so we cannot solve for very higher, so like not for very high, like we cannot even solve for fifth order of polynomial, find the root of the fifth order of polynomial, but here this is a cubic polynomial and we can find the solutions. So now the solution is again to find the eigenvalues, we again solve the characteristic equation. Okay, so this is the characteristic equation, the determinant of the whole object, and we have to solve for energy E. Okay, so you go on and calculate the determinant, and after that you will see that you end up with a second degree polynomial of E. Okay, so one of the E actually gets factored out, so this E1 minus E that gets factored out, so that gives you one of the solutions. Okay, so now I am left with 3 other solutions, right, because this is a cubic polynomial. Okay, so one solution is E is equal to E1, and then I have a this equation for which I can use the quadratic polynomials roots equation, and we will be able to find that okay, this is given by some simple form like E1 minus E2 square plus 4A mod square plus 4B mod square. Okay, so now in the perturbation theory we are assuming that these A and B's are small, and also they are mod square, and when they are summed up they are also very small than our E1 minus E2 square. Okay, so then what I will do is I will take this E1 minus E2 square out of this square root, and then this whole quantity will be very, very smaller than 1, and when that is the condition I can expand the square root. I can write the Taylor series for this square root. So Taylor series for the square root is, as you are aware of, is 1 plus half x plus so on and so forth. Okay, I just want the I just need the first order here, so I will not look into next higher orders. So this is when you expand this square root. okay, up to first order, and you do some algebra and do some simplifications, and you will see that your energy E2 will one of the energies will become E2 plus a mod square plus b mod square by E2 minus 1. So this is the E3 that we calculated lastly, right? So for the using this non-degenerate perturbation theory, so E3 actually matches exactly. So this calculation is okay. Now we see that one of the energy, so which was like a degenerate energy, that doesn't change. Okay, so this is the same agreement that we reached after doing our last calculation using the perturbation theory. So this also matches, and you will see that this also matches. Okay, so our degenerate perturbation theory calculation actually matches exactly with our exact eigenvalues when we expand up to some order. Okay, but we can also think like what is wrong with using non-degenerate perturbation theory here for all of the states. Okay, so you can actually check that the result you will get from non-degenerate perturbation theory will not blow up. So like, because these elements are 0, your calculation will not give you infinities, but you will see that the result you get at the end of the day doesn't match with the exact eigenvalues or the calculation from degenerate perturbation theory. So you can check that. Okay, so whenever there is degeneracy in the system, it is a good idea to always use degenerate perturbation theory. First calculate the first order. If it vanishes, then go on to the second order. Okay, but if you get some non-vanishing contribution from the first order also, you just stick to that. That is your lowest order contribution, and you can do further more calculations with that part of energy calculation. Okay, so this is how one deals with this degenerate perturbation theory. Okay, so is this okay? Any question? So if not, then let us move on to the next question, question 2. So now we are given a Hamiltonian like this. Okay, so this Hamiltonian, the first two part we know, right? The first two part, so the solutions for the first two part like is just a spherical, this is just your LM kit. Okay, so and now there is additional part which is given by CLY, where this perturbation assumption is, so B is much larger than C. So C is some kind of magnetic field which we have applied. Okay, and this is our total Hamiltonian. So first of all, let us segregate our H0 and V. Okay, so H0 will be only this part. Okay, and we can solve this equation. So the L square and LZ square, they commute and they have same set of eigenvectors, which we know from our angular momentum discussions that this is just L comma M. This is the state or eigenstate of this Hamiltonian H0. Okay, but once you plug in this Ly, it doesn't commute with this L square, this Lz actually. So we have to do some sort of perturbation theory. Okay, to get the corrections to these energies order by order. Okay, so this Ly can be written in terms of this ladder operators L plus and N minus. So L plus increases the this M quantum number, and L minus decreases the M quantum number. Okay, so so the given info is like the L plus. If you take this matrix elements of this L plus, you will get something like this as a coefficient, and this matrix element will be non-zero only when L prime is same as L. So this is the Kronecker delta. Okay, which comes from the orthonormal properties of these LM states. So this will be non-zero only when this L prime and L will be same, and M prime will have to same as M plus 1. So why this is the case? So that's because the L plus has already increased M by M plus 1, right? And then when we are taking the inner product with another M prime, so then that M prime have to match with M plus 1. Otherwise, from the orthonormal properties of LM, those quantities will become 0. So that's why there are this Kronecker deltas are there here. Okay, so for L minus m, rather than m plus m, this becomes m minus 1. Okay, so these are the matrix elements that we need for this calculation. So the derivation of this is very easy. You can look into any textbook, or you can start from very first principle, and you will be able to derive this very easily. So my Ly is given in terms of L plus and L minus divided by 2i. Okay, so the first order contribution, so when you look into first order contribution, we look only to the diagonal elements of that matrix. Okay, so here the matrix is given by C times the Ly, which is the perturbation in our Hamiltonian, and we look into this diagonal, right? So the diagonal will tell me that okay, what are the corrections to the first order. So in the first order, because this Ly only has this ladder operators, right? So whenever you have any ladder operators and you take the expectation value of that ladder operator, that always vanishes. So why is that? Because L will increase m by m plus 1, but this is the m, right? This is not m plus 1. So when you will take inner product of m and m plus 1, that quantity becomes 0. So the same thing will happen here also, but here L minus will decrease m with m to be m minus 1, but then we are again taking overlap with m, right? So, and m minus 1 states are orthogonal states. So when we take inner product of those states, that vanishes. Okay, so this is so basically from very simple argument we see that the first order contribution is 0. Okay, so then we'll have to go on and we have to calculate the second order. So for the second order, we need rest of the matrix elements. Okay, we don't need the diagonals anymore. So only diagonal elements contribute to the first order in perturbation series, and for this next second order, all of the other off diagonal elements of this matrix they start contributing. Okay, so Ly, so I have separated L in terms of L plus and L minus. Okay, and I have just taken inner product of the I have taken matrix elements of these L plus and L minus operators. Okay, so here I have used this aforementioned identity or this matrix elements equation of L plus, which gives me this and this. Okay, and I have to square this whole thing. Now when I square this, you will see that because of Kronecker delta, only this term will survive and this term will survive, and they will get squared. Okay, so that's why you see that there is no square root anymore. So this is the whole quantity for the coming from the first term, and this is the second quantity. Yeah, go on. Right. But in the case of second order, it doesn't vanish. L plus L minus. So yeah. So like I'm telling, I was saying that if you have some kind of ladder operator, okay, and you take expectation values on some psi and psi. So expectation, when you take expectation, we say that okay, the bra and the ket are exactly same. Okay, if that is the case, then anything will become 0. But other elements like psi 1, L plus minus, psi 2, they are not 0 by default. Okay, so the diagonals are 0, but the off diagonals of this matrix of this operator, they might not be 0 in general. Okay, so in second order, only the off diagonals of that matrix contributes. So does that answer your question? Okay, so that's why in second order we are only interested in the off diagonal elements, right? So like we are calculating this kind of off diagonal elements here, and like this is a bit of algebra, and when you will do this algebra, you will see that okay, you arrive here. All right, so then after doing that, so now let's write the perturbation expression, right? So E in so 2 in the power in the bracket, that means it is in the second order. So the correction is in the second order, and then there is LM, means that we are talking about what correction happens to the LM state. Okay, that kind of state. Okay, so there is one additional C square. So because this is in the second order perturbation, so this is the quantity, right? So this is my off diagonal elements of the matrix. Okay, and divided by ELM minus EL prime M prime. So from this expression, so you can look at any second order perturbation theory expression, you will clearly see that because the numerator if if Lm will become same as L prime M prime, the numerator will diverge. That will become 0, and in turn the whole expression will diverge, and you will get some ill-defined results, right? So to restrict that, how it comes out that, yeah, go on.
Sir, I have a question.
Yeah.
Sir, you have just now said that these, the diagonal elements contribute to the first order and off diagonal contributes to the second order.
Right.
Sir, sir, in that case, can we if we know the matrix form of Ly, can we find the eigenvalues from there and claim them to be the first order and second order corrections?
No. So that will not be the case, because you see, I am not exactly calculating the eigenvalues of Ly. Okay. So I have a basis of my initial H naught Hamiltonian. The Hamiltonian which I know all of the eigenvalues and all of the eigenstates of, right? So I know all of these eigenstates like Lm, and I know the Elm, what are the energies of those corresponding eigenstates. Okay. So I am not now I have this additional Ly operator. Okay, now what I am looking into is, now I have these Lm states, and I am taking different kind of matrix elements of that Ly operator, and I am doing some calculation. Okay.
Yes, sir. I am saying that if we know the matrix representation of Ly on the Lm basis,
yeah.
then can we do that?
Yeah, then you can do that. So this Ly, normally Ly, yeah, so you have to first write this in the basis of Lm. Okay, then you can write down, but you will see very quickly that when you have this Ly in Lm basis, you will see that there are diagonal elements and there are off diagonal elements also, which will contribute to your first order and second order respectively. Okay, so it is not like we are calculating the eigenvalues of this perturbation Hamiltonian. It is like we are taking the Ly and we are writing this in the we are finding out all of the matrix elements, right, which is same as writing that particular operator into this Lm basis. So you are absolutely correct about that. So you will get some diagonal and off diagonal elements, and that they will give different corrections.
If it most probably to the 3 cross 3 matrix,
right?
The diagonal, there will be 3 diagonal elements. So do we sum the first order?
No, so like here I am not assuming any L. So this is like very general. So I can give you any L. So I am not writing any matrix representation of operators. So I am just using their algebras. Okay, so which is actually much more general than like you are saying that you can obviously go and do all these things for when L is 3. But all of these statements, all of these calculations are much more general, and they hold for any L. Okay. So these are like more abstract kind of calculations. Okay, so this is the second order correction, and you see very well that the denominator actually diverges. Okay, if Lm becomes same as Lm, so in this summation Lm is different than L prime M prime. So we can plug in this matrix element, okay, in this expression, and so after doing some little algebra, and you can also sum over some indices like L prime and M prime, because these are Kronecker deltas. Okay, and Kronecker delta will make only few elements non-zero, right? When L will be same as L prime in this whole summation, then that term will be non-zero, and when M prime will be same as M plus 1, that term will be non-zero. Okay, and similarly when M prime will be M minus 1 in the second term, only that term will be non-zero. Okay, so with this kind of argument, we are summing over L prime and M primes also. Okay, so now we are only left with this expression. Okay, and you see that on the denominator there is ELM and ELM plus 1, and so just let me show you how to calculate the eigenvalues of this H naught. So H naught, because we know that all of the eigenstates are L and M, so when L square acts on this Lm, so that gives you H bar square L into L plus 1 Lm, right? And when Lz acts on Lm, this gives you H bar M Lm. Okay, so you use that equation, and you will be able to find out that this energy becomes something like this: A L into L plus 1 Bm. So here I have let's say I have absorbed the H in this A's. Okay, so I am not writing H's anymore, A and B's. Okay, so this is the energy that we will find. So now you can plug this energy into your expression of the second order perturbation. Okay, so you can plug those things. You will see that many things will cancel out. Okay, and you will see that for a given okay, so there will be also a C. So if you start for a given L, there will be only this very simple expression. Okay, very simple correction. Okay, so it's a good idea to check all of these things yourself and get a taste of how to do this kind of calculation, this kind of matrix element calculation, or second higher order perturbation calculations. Okay, so just to get a flavor of how to do these things. Is this okay? I mean, so all the steps, so mostly these are algebras, but the philosophy of this calculation, is this okay? Like, I mean, do you get the point? I mean, which I am trying to make. I mean, like, we have to do order by order. Because our first order was 0, so we have to go on and calculate the second order. Okay, so I mean, this is the main idea which we mainly do when doing perturbation calculations. So any questions? Okay, so if not, then let's move on to the next problem. So this is about quadratic Zeman effect. Okay, so normally you will see that this kind of Hamiltonian, this kind of terms are there, but these are very small. These are called diamagnetic terms. Okay, so this is in order a square. So this is very small, and normally we neglect this term when doing any calculation in this in the hydrogen atoms Hamiltonian. So this A here is the vector potential, okay, which is because of there is a constant magnetic field. Okay, that's the Zeman effect, right? So there is a constant magnetic field in the background, and you introduce vector potentials in your Hamiltonian, and I mean, that's how the system couples with the external magnetic field. Okay, so now the coupling is square in our case. So you can calculate that, okay, for a constant B in let's say z direction, what is the vector potential that we have to use. Okay, so you will see that this is not a unique definition, but this is something called a symmetric choice of the vector potential. You can do with different things, but for different kind of calculation, or if you are interested in different symmetries, for example, in this case we have a spherical symmetry, we have a rotational symmetry, and we do not want to bother it, so we are taking a symmetric kind of combination, which is y and x minus yi plus xj cap. Okay, and now we are asking that if this is your your ground state, then what is the first order correction in your energy in the ground state. Okay, so and also if we write our Hamiltonian in this form, so this chi is also a very important quantity, which is called the diamagnetic susceptibility. Okay, so this kind of quantity is like so if there was a linear order, then there will be something like some chi 1 b. Okay, so if there is some other order, some chi 3 b cube. Okay, so these coefficients, these chi coefficients are called susceptibilities, and this they tell you they give you many information about the systems. So these are called response functions. Okay, so but yeah, probably we'll talk about that some next week or so on probably. But let's just try to calculate this quantity. Okay, so A is given by so A square you can calculate. This is just taking a dot product of A with itself, that gives you B square by 4 and X square plus Y square. Okay, and because we are in a 3 dimension, and in 3 dimensional we know that for polar coordinate system we use X as r sine theta cos phi and Y as r sine theta sin phi. Okay, so if that is the case, then you plug those x and y's in your expression, and you find out that this x square plus y square is just r square sine square theta. So now your total Hamiltonian reads something like this. Okay, so there are some constant factors sitting here, and this r square and sine square theta, these are the coordinates of this hydrogen atom. Okay, now I am writing all of these things. I do not want to bother too much about those things. I am writing those as q. Okay, so I'll then restore q at the end of the result. Okay, so q is just e square b square by 8 mec square. Now what I want to do is I want to calculate the expectation value, it is the like diagonal element of this HP in the ground state. Okay, so this is the first correction I want to look into, because so like I mentioned in the last problem. So in that problem, what we have is we have this whole measure of the integral. So this is called measure of the integral. So here are r square dr, sine theta d theta and d phi, because we are doing in a spherical polar coordinate. So the integrations, any 3D integration we'll have to write this part. Any 3D integration we do for in a spherical polar coordinate. Okay, so or you can also think in terms of Jacobian. So if we have like dx, dy, dz, and we want to go to, let's say, spherical polar coordinate, then it becomes some Jacobian times dr, d theta, d phi. Okay, now in this case the Jacobian is also a function of r, theta and phi, and the Jacobian turns out to be r square sine theta. Okay, so this is the Jacobian in this case. Okay, so now we are in the polar coordinate system and we have all of these things, and we will do integration one by one to all of those things. Okay, so now to do this kind of integrations, so it is a very important identity that you should remember. So these are the gamma functions. Okay, so if you have some integration of x to the power z minus 1 times e to the power minus x dz, and where you are okay, this is just dx, and where you are doing the integration over whole positive space 0 to infinity. So then you can write this integration as a gamma function, gamma z, and if there is any coefficient sitting there, that also becomes a to the power z. Okay, so same power z, and this becomes also a to the power z, and this gamma function is nothing but a fancy way of writing the factorial. So this gamma becomes z minus 1 factorial by a to the power z. So we will very soon use this identity. Okay, so now let's collect all of these terms which is r dependence. Okay, so I can separate out all of the r dependence from this integral. So which becomes, so one r square is here, and there is another r square which came from the a square, right? So so now I have r to the power 4, and there is e to the power minus 2r by a naught which came from the wave function, and this integration goes from 0 to infinity. Okay, so now this matches very well with this kind of integration, right? Now we'll just use those use this identity, and you see that whenever this is 4, then I have to write 4 plus 1, so this is gamma 5. Gamma 5 means 4 factorial, so gamma 5 divided by 2 by a naught to the power 5. Okay, so and there is also this integral over d phi, but we see that there is no function of phi in this case, right? So this just becomes 2 pi. Okay, so that's what I have written here. And there is lastly the sine theta cube integration of 0 to 2 pi, 0 to pi. Okay, so now whenever we have this kind of integration, so for spherical coordinate systems, it is a good idea to convert all of these things in cosines. Okay, so in cosines, whenever these are cosines, this becomes very very simple. Like, so I am writing d theta and one of the psi theta as d cos theta. Okay, and there will be additional minus. Okay, and the minus actually at the end of the day minus goes away, so I am not writing the minus, and there will be additional sine squared theta, and we know that sine squared theta is 1 minus cos squared theta. Okay, and you will write the limits of cos theta from 0 to pi, and that's how I will replace this thing, and you will see that at the end there will be a minus which will actually go away. So this integration is nothing but like this cos theta here becomes something like a dummy variable. So like we can just evaluate this simple integration, right? Dx 1 minus x square. Okay, so I am replacing cos theta by x. Okay, but because cos theta here just is a dummy variable kind of thing. So you can do this integration very easily, and this gives you the 4 by 3. Okay, so now this is 4 by 3. So now you put in all of the things you have. Okay, so you see that all of these things will actually cancel, and you will be left with q. So q was my initial constant, so I have packed up many constant. I have called it q, right? And now I am left with a naught square. So a naught is a naught is the Bohr radius, right? So now I am left with this quantity. Okay, now I'll insert this q. Okay, and you see that this this whole expression, so this will become like this is a quadratic in b square, which signifies okay, so this is just a quadratic in b square, right? And then we'll write again this part as some minus half chi times b square. So here this chi, I have added an additional minus here also, so is just this. Okay, so this is one simple kind of calculation for perturbation in hydrogen atom, right? So you can make variations of this, you can add different kind of perturbations, and you can try to solve those things. Okay, these are kind of like, these things look scary, but they are not that much scary. So if you use this kind of identities like gamma functions, and you convert all of these signs into cosines, okay, you will see that these integrations are very much tractable, and these are kind of not that hard. Okay, so this is like one of the example of how to do perturbations in HP. So how to do perturbation in hydrogen atom. So you have done already some examples, like you have done Stark effect in first order and also in second order, right? So that is also another example of perturbation in hydrogen atom. Okay, so any question? Okay, if not, then let me move on to the next problem. So now let's talk a little bit about variational principle. Okay, so in variational principle, so like I have mentioned this before also, so most of the quantum mechanics problem we cannot solve exactly. Okay, so if we cannot solve exactly, then we have to do approximations. So for example, you have already seen some examples of how to do some perturbation examples, right? So when you can identify the Hamiltonian for which you know the eigenvalue like h naught, and you can also identify another Hamiltonian with a small parameter that you can call the perturbation, then only perturbation works out. But if the other Hamiltonian is not doesn't have a small parameter, then the perturbation doesn't work out at all. Okay, and in some cases it might happen that you have given a Hamiltonian and you cannot separate that Hamiltonian into a h naught for which you know the eigenvalues and eigenvectors, and into some h1.
Sir, could you please repeat?
Yeah.
Sorry to say, could you please repeat?
Which part do you want me to repeat?
What you said just now.
Oh, okay. Yeah. Okay. So let.
From perturbation to variational principle.
Yeah. So I was saying that in most of the cases we cannot solve quantum mechanical systems exactly. Like we cannot solve Schrodinger equation for most of the cases, because things become non-linear and we do not know a closed form of those things. Now what we do is we resort to some approximate methods. Okay, so approximate methods are like we are doing now, which is perturbation theory, or there is also variational principle, and there is also WKB approximation, which is also an approximate method. Okay, so so when you do perturbation is like when we are given a Hamiltonian, and that Hamiltonian can be broken into two parts, like some so let me just write here. So Hamiltonian can be broken into two parts, for example, so h, let's say you have given a h, and you can write this h naught plus some lambda h1. Okay, so let's say you can write it, and this lambda is the small parameter. Okay, so then only you can do the perturbation theory, and the perturbation gives you kind of accurate results order by order. Okay, but let's say I am giving you some other Hamiltonian for which you cannot separate it out, or let's say you have some h naught plus some alpha h1, but alpha is not so small. Okay, so if it is not so small, then we cannot write the perturbation series. The perturbation series will diverge, so we will not get physical results. Okay, so perturbation will not work. So I mean perturbation theory will not work. Now there can be another scenario also where you are given a Hamiltonian, okay, but you cannot separate it out, cannot separate in terms of h naught and some alpha h1. Okay, so I am assuming here that for h naught we know all of the states and the eigenvalues. So h naught I can exactly solve. Okay, but let's say I am giving a Hamiltonian for which you don't even have a h naught. Okay, so then, and then you cannot do any perturbation theory, right? Because to do perturbation theory, you have to have H naught, you have to know some eigenvalues, some eigenvectors, okay? Then you can do series, you can calculate matrix elements and so on and so forth, okay? But for a generic H, you cannot even do any of this, okay? So now the idea is, let's say you have given a general H and make a good guess. Of the state, okay? We have to depending on the physical system, depending on the symmetry of the system, you have to make a really good guess if you want to get a good answer to the ground state energy, okay? So you have to make a very good guess, okay? And then you can write the expectation value, okay? So this will give you some energy, okay? Some energy, and let's say these are some parameters alpha, and then you will calculate this derivative with alpha, and you try to, for which alpha does it minimize the energy, okay? So this is the gist of the variational principle. So here I do not need any H naught, I am not doing any perturbations, but I have to come up with a very good guess of the state.
Okay, sir, I have one more question.
Yeah.
I would like to add something.
Right.
Sir, so it means that like perturbation theory, like first order, second order perturbation theory, we won't be having any kind of first order, second order, just a variational principle.
Right. So the energy you get, the energy from this calculation you get might not be very accurate, okay? But this is bounded by below, like if this is your energy after doing this variational calculation, and this is your original ground state, okay, which you know from some experiments. Let's say you can let's say measure the ground state energy, okay? So it is bounded from below the ground, bounded by the ground state from below the E alpha, okay? That is the main property of this thing, okay? So you cannot go below this thing, you cannot go below ground state. So quantum mechanics, this superposition principle or the completeness of the base is restrictive from doing that, okay? So this gives you a kind of lower bound to the ground state energy, which you can have, okay? Now if you want to do better, like you were asking, like, okay, this can you do first order, second order? We cannot, there is no notion of this kind of orders, but there is notion of, like, you can have some wave function with one parameter that will give you some results, but you can write some wave function with let's say 100 of parameters, which people do in the research, okay? People write 100 parameters and they will minimize respect to all of these parameters, okay? So more parameters you write, a more good guess you write of the state you write, you can go very close to the ground state, okay? So this is the idea. So you can do with one. So for all our textbook problems, like we look into Griffith or like different textbooks, we only take one or let's say two variational parameters, okay? We just do variation with respect to those parameters, but in general you can take thousands of those parameters and you can minimize respect to all of those. In principle, if you have n plus 1 number of variational parameter, that will give you a little better answer than using n variational parameters, okay? So that is the idea. So that is the kind of quote unquote order kind of notion you can have, okay? But there is no order by order expansion in this case. So this is the main idea of variational calculus. Now is the philosophy of this variational calculus clear? I mean, when you want to do variational calculus, variational principle, or when you want to do perturbation, I mean, there is a clear distinction, right? So is this clear? Any doubt? Yeah.
Sir, then sir, in terms of Stark effect, so if we make a guess, can we consider electric field to a parameter?
Yeah. No. So it is not like that. So in start effect, what you do? So okay, so we'll see some few explicit examples, but in the Stark effect, that is not a free parameter. Like, that is, you are giving some explicit electric field from outside. So that is in your Hamiltonian. So let's say your Hamiltonian depends on some parameter like A, B, C, and so on and so forth. Okay, but we are not talking about these parameters. So we'll have to come up with a guess with psi, which is, let's say, parameter of alpha, beta, gamma, which are different parameters. And then we calculate the expectation value on that state, and we will have to minimize with respect to alpha, beta, and gamma, all of these three things simultaneously.
Sir, how do you find out this alpha, beta, gamma?
Yeah, so that's it. So that is the recipe of this variational calculus, variational principle, right? So we'll see some few examples of this. How do we calculate the alpha beta? Yeah, so that is, yeah. So okay, so you have H ABC, right? And then you are taking with psi alpha beta gamma and psi alpha beta and gamma, okay? And there is, let's say this is normalized, so I'm not dividing with any denominator, okay? So now this is some function which has alpha beta and gamma as variational parameters, and it also depends on ABC, which ABC are not free parameters. These are physical parameters. These come from environment or some couplings or the electrons mass, like these are not variables. So now if these are the things, so I want to minimize, like any minimization problem, what we do is we take this derivatives and we make that to be 0, okay? And right, so in this case, if we have three parameters, variational parameters, we have three such equations, okay? So now we have to spontaneously solve these three equations and find solutions for alpha, beta and gamma. So this is how we find alpha, beta, gamma, that minimizes or that extremizes this expectation value. And yeah.
So these parameters are the values that you obtain for the alpha, beta, gamma. These are at those values.
Yeah.
Energy will be minimized.
Yeah. This right. The energy will be extremized. Right. Yeah. Right. Exactly.
Energy will be minimized, right?
Yeah. So that is this condition tells, right? So if there is a maxima of a maxima or minima of a function, then the derivative becomes 0.
Yeah, we are finding just the value of the variation parameter.
Yeah. So so and
How do we know the physical quantity which is related to the
no.
which physical quantity would be the
So
parameter?
this alpha beta. So okay. So now when you have obtained the solution, yeah. No. This is not abstract. So when you have obtained, when you have solved these three equations simultaneously, you will see that this alpha becomes a function of A, B and C, which are the parameters of the Hamiltonian. Beta becomes a function of A, B and C. Gamma becomes a parameter of A, B and C. Okay, so this in turn depends on the this Hamiltonian's parameters, right? So I mean, yeah, so we'll do, I mean, I can see we have some confusion, but when we'll do few examples, this will become crystal clear, absolutely clear. Okay, so yeah, then we can discuss if you have some other doubts. Okay, so let us actually try to do few calculation of variational principle. So I have come up with few kind of potentials. Okay, so one potential has a mod x. Okay, so mod x is the event function, and there is a cusp singularity. You cannot take a derivative here. Okay, there is a cusp singularity in this potential. This is x to the power 4. So this is like x square, but x to the power 4 is like little bit stretched. Okay, and one other example is that one of the side is actually infinity. There is a hard wall, and one other side is linear. Okay, so these are the three examples that I have come up with, and so we'll see that how we'll do variation principle for all of these three things. Okay, and it will become absolutely clear what do you mean by all of these things. Okay, so first of all, we have to choose a state, right? So let us talk a little bit about how to choose a good state. So now let's say you have given a potential something like this, okay, and you want to guess a ground state. So now, I mean, you can take this statement as a kind of a principle. In any ground state, it will have a minimum nodes. It will have no nodes. So like if I want to come up with a ground state, it better be a bell-shaped curve, something like this. Okay. So the form can be different. The form can be something like some e to the power minus ax square, or it can be also some a square plus x square, some form. So this is called the Gaussian, and this is called a Lorentzian. Or you can also take something like E alpha A mod x. So this doesn't have a name. So you can do different things which has no node in the ground state. Okay. So only you have to ensure that the psi x and d psi dx at x tending to plus minus infinity, they vanish. They become 0. So this is the things that you have to maintain. Otherwise, you will not be able to normalize these quantities, right? These are the basic requirement from quantum mechanics. Okay. So we are assuming, okay, there is a we have to come up with a good ground state. So you can take any of this Okay, you can take any of these states and you can plug into that Hamiltonian. You can calculate the expectation value. Okay, so yeah, so that is what I wanted to say. So like in this example, so I have taken this kind of Gaussian state. Okay, so you can take Lorentzian, anything. Okay, so I have taken a Gaussian state. Okay, and this a by pi square root comes because of normalization of the state. Okay, so first you take a good guess depending on the symmetry, depending on how the quantum well looks like, and then you have to normalize this whole wave function, right? If you do not normalize, then there is no meaning of doing any calculation. All of the probabilistic interpretation, they don't make sense anymore. Okay, so you have to normalize wave functions first, and then you have to take the expectation value over this whole Hamiltonian. Okay, so let's do it part by part. So let's first look into what happens to the expectation of p square. Okay, so you see p square, like this kinetic energy part will be same for all of these things. So let's just calculate it once. Okay, so let's first calculate p square average. So p square average in this state psi. Okay, psi is this one. This is my initial guess. So now because this p is a Hermitian operator, so I can take one of the p to this side, right? Now this becomes p psi and p psi in both in the bra and kets. Okay, so when you do that, this basically becomes the norm of this vector. Okay, so I do not want to keep p square here because p square is, too much work to do. We have to take derivative twice. But if we just do this step, now this whole thing reduces to taking derivative once and taking the whole mod square. So now, so this is the quantity, right? So this is my p operator, and this is the psi x. Okay, and this has to be squared. So you can go and calculate this del psi x, this is simple derivatives. Okay, the simple derivative, then you will see that you will end up with something like this. So this doesn't look like gamma functions, right? But these are, you can also try to look into this identity. So if you have something like this, 0 to infinity 2 x to the power 2z minus 1 e to the minus a z square dz, now this will also give you gamma z, a to the power z. So these identities of gamma function are very useful in this kind of calculations, right? So so this is the identity that we'll be using, and we'll be matching this quantity with this form. Okay, so if we do that, then this quantity will give you gamma 3 by 2. Okay, so gamma 3 by 2 is, it is not kind of a factorial, right? You cannot take a factorial of a fractional number. So but 3 by 2 you can just write in gamma any n by 2. This is basically n minus 1 by 2, n minus 2 by 2, and so on and so forth. And at the last you end with half and square root pi. So this is the formula for any gamma function. Whenever the argument is n by 2, integer by 2. So now you use that, and so like you see that for 3 by 2, gamma 3 by 2, what I have written is, I have written half and square root pi. Okay, the last element will be square root pi. So some of the things actually cancel. Okay, and I am left with only this part. So this is my p square average. Okay, I am done with p square averaging, and now I have to deal with the potential. Okay, so the potential in this case is given by f mod x. Okay, so f mod x is just, I have inserted it here, and then because this is a mod and all of the things are even function inside, so I'll just take this limit 0 to infinity and I'll multiply 2. Okay, now you are familiar with this thing, like I have just written down this identity of gamma function. So this you write in terms of gamma function, and this becomes gamma 1 by a. Okay, so the whole expectation value becomes f by a. Okay, so just to recap, this is the p square average. This is the p square average. Okay, my screen got stuck probably. Just let me check it. All right. Yeah, so I have obtained p square average and I have obtained v's average. So I have all of the ingredients to calculate the h's average, right? So h's average is p square by 2m, p square average by 2m, and then there is vx. Okay, so now this is the simplest thing. Everything boils down to this. Okay, so you see what I have done here is, so I have added h square. Okay, because this momentum operator has h, and we are calculating p square, so there is an 1 h square, okay, and this is these are the things which came from the p square average, okay, and additionally there is also f by a, okay, which is from the potential. So now what we will do is we will take the derivative of this Hamiltonian with respect to the a, okay, a is our variational parameter in this case, and we will make it to be 0, right, okay, so we will make it to be 0 and solve for a, okay. So these are some not so tedious but some algebras you have to go through. You will see that the Hamiltonian actually boils down to something like this. So there was a, okay, so this is the energy of the Hamiltonian in the ground state, I mean in this variational ground state, and I have inserted the value of a, which I have obtained by minimizing this del h, h expectation, okay. So this is your Hamiltonian, okay. So after doing all of this calculation, this is your Hamiltonian. This is your energy in this kind of variational state, okay. So does that make sense? Is this clear? So this is just some simple calculus, right? Maxima, minima finding. So yeah. So now you can also go ahead and calculate for different potential, like fx is x to the 4. So this is also similar. You have to use gamma functions identities, okay. So this note will be available to you later on, so you can look into this later on, or you can do it yourself, okay. So like the calculation goes here also similar. You calculate h, here it depends on a, right, and you minimize with respect to a, okay. So that is the thing that you have to do. So now I would like to discuss one of this thing, like I would discuss this potential. So in this potential, you see that I am not taking a bell-shaped curve, right? So the bell-shaped curve would be something like, so I am not taking any bell-shaped curve here, okay? So, so in this case, so a good solution, a good initial guess is not a guess which has a bell shape, okay? So why is that? Because I have one hard wall sitting here. So this is the hard wall, and I have to make sure that any solution that I come up with becomes 0 at that point, okay. So one way to do this is you just multiply 1x with your this Gaussian kind of thing, okay. So that will give you a something like it becomes 0, and then at infinity it also becomes 0, okay. So this will give you some nice features like what you want to have in this in the state, in the ground state of this Hamiltonian, okay. So now you can take this thing and you can do the same calculation. You can calculate the p expectation, p average p square expectation. You can calculate the vx expectation, okay, and you can calculate the h, total h. So the total h, after doing the total h, the total h looks kind of simple. Expectation looks very simple. So then you take derivative with respect to a, okay, and then you just solve for a. That's all. Okay, so then you find out, okay, these are what are the solutions, okay. So I mean you should do some of these calculations, okay, just to get a taste of how to do this variational calculation, okay. So yeah, I'll discuss one more problem, okay, probably not this hydrogen one. So let me discuss one another problem. So let's talk about so we have been talking about variational principles for calculating expectation values of the ground state only, right? So but in principle you can also calculate energies of the excited states, okay. So how to do that? Now to do that, so you see initially what we started is we have to come up with a good guess. So ground state generally doesn't have any nodes, okay. So the first figure doesn't have any node, so it has 0 nodes. So it is a good candidate for a ground state. So it can be a Gaussian, it can be Lorentzian, okay. But if you want to, let's say, calculate for the first excited state, then what should we do? So we should actually increase the node, okay, and our solution, our trial solution should have at least one node to get the expectation value of this first energy, first excited state, okay. So now you can also go on and you can multiply just x, okay, that will introduce a node here. So now to get the energy, variational energy of the second excited state, you have to multiply, you have to introduce two nodes to this Hamiltonian. Okay, so like for example in this case, for the Gaussian at least, the x squared does the job, so it will introduce two nodes. So now if you calculate your expectation values with these states, and you have your variational parameter as a, and you do all of this calculation, minimize with respect to a and find the value of a, you will see that you get kind of good agreement with this, not very good, but kind of some estimation of what should be the first excited state's energy, what should be the second excited state's energy. So yeah, so you can also find out, you can introduce many more variational parameters to calculate the energies for like you can n number of variational parameters to get a better estimate, right? So this is the idea about variational principle. And yeah, so this will be it. So any questions?
Yes, sir, I have a question.
Yeah.
Sir, for excited state, we can also follow the ground-smooth observation procedure for keeping the excited state, right? Using the trial function.
Yeah.
Once we know the ground, suppose we have a case of the ground state trial function, okay?
Okay.
For the excited state, what we need to do is that the second case, the case for the first excited state or the second excited state, must be orthogonal to the ground state.
Yeah. So the case doesn't have to be orthogonal. Okay, the case doesn't, because these are not the exact eigenstates of the Hamiltonian. These are what you are coming up with. Okay, so like in this case, these are not orthogonal to each other, but that will give you some estimation. So now we are talking about estimations. But if you want to get a orthogonal state, then you have to apply some something called Gram-Schmidt orthogonalization. Okay, you have to orthogonalize these states. Like we are estimating the energies, right? We are not saying that we are not saying that these gases will make a complete set of bases. We are not saying that. That is a very, that we cannot do actually. So we are saying, okay, I want to estimate what are the energy states of first excited, second excited, and so on, and this will give me some sort of estimation. Okay, so this will not be this will not form a complete basis. Now, if you want to make it orthogonal, you can do Gram-Schmidt orthogonalization. But yeah, so you will have to find out all of this, all of the states you can have, and you have to Gram-Schmidt all of them. That is it. That is too much work. But we do not want to do that. So with this thing, we just want to estimate what are the energies. Okay.
One more question.
Yeah.
The statement that is written, nth eigenset as n node.
Yeah.
This is generally an observation, right? Can be proved.
This is an empirical kind of thing. I am not aware of any proof. This is an empirical thing. So we see that, okay, this happens with all quantum systems. Okay. Generally, the lowest node will have the lowest energy state will have the lowest number of nodes, which is 0 nodes. Okay. So like you see all examples that you can find in textbooks or in some research papers. You see all of them have like 1 by 1 nodes are increasing. For 2D, 3D, all of these things, it makes sense. Okay. So the nodes increases the curvature. The Schrodinger equation, the d2 psi dx2, this is the curvature of your state, and as you will increase the curvature, that will increase in turn your energy. So that is the main idea behind this. But there is no proof of this thing. This is an empirical fact. Yeah. So yeah. So yeah. So okay. So let me just yeah. Okay, so Schrodinger equation has this kind of term, right? Okay, so this right. So if you're psi, you will have much more nodes, so it will have to curve much more faster, right? So it will have to you have to give more curvature to your states, so then only you can get some excited state. So that is the idea.
Also, what we are doing so far, this approximate method,
Yeah.
we are doing for closed quantum systems, right?
These are all quantum. Yeah, these are all closed quantum systems. Yeah. So for open quantum system, there are formulations which are completely different. Okay, there are something called Lindbladian. People do with Lindbladian. There are some, you can do some things, some approximations, some perturbations. But in your quantum mechanics 1 and quantum mechanics 2, this is out of the course of these courses. Like open quantum systems are out of. You cannot just study these things in like basic quantum mechanics. So there are theories. There are all of these things, formulations for open quantum systems. These are called Lindbladian formulation. You can look it up. So yeah, so that is it. Okay, so any more questions? So if not, so this session is recorded and this will be available on, so you will have the link of this session, and these notes will also you will get access to these notes also. Okay, so if you don't have any more questions, then I guess we will finish today and we'll meet next week and we'll solve more problems. Okay, so yeah, so have a good weekend. Yeah, yeah, okay.
How are the assignments marked? Could you please just tell me?
I don't have any information regarding this. Yeah, I don't have any information regarding this. Sorry, I cannot help you regarding that. So for that, I think you should talk to NPTEL office. They will give you some clarity into this matter.
Subjective based.
Yeah.
Assignments are subjective.
Right.
That's why I'm asking.
Yeah, I guess there should be step markings. I guess if you are asking about that, I guess there should be step markings, but I'm not totally sure about that. Okay, so I mean, if you want a really good answer, I think you should write to NPTEL office. They can give you some clarity into this topic. Okay then. So have a good weekend. I'll see you next week. Okay.